Okay. Okay. So uh, last time we ended with calculating the circumference of the hyperbolic ball. Uh, so if you take a hyperbolic ball of radius beta centered around 0, then your circumference will be 2 pi sine hyperbolic beta. So sine is sort of an exponential function. So last time, as I mentioned, this is kind of because of the curvature being -1. Your circumference kind of grows exponentially. If the curvature was positive, the circumference would grow lower than linear. So linear would be for zero curvature. So if you had positive curvature, this would grow in a slower fashion. Okay. Okay. So. Okay. So this is an important theorem here. So we have already seen that PSL2R, which are Mobius transforms which preserve the upper half space, they are isometries of this hyperbolic space. But the claim is now that these are all the isometries, all the orientation preserving isometries. Okay, so first. Okay, we know this. Now we have to prove the other inclusion. Okay, so take any element of this isometry. So this is a diffeomorphism from H to H, but it can also be considered as a map from D to D. So this you will do by just pre-composing by something and post-composing by the inverse of the same thing. I should actually say this is a different map, but I will use just abuse the notation right now. So one fact we should know is So isometries preserve angles. This is because the angle is given by the inner product, and isometries preserve the inner product, so it preserves angle. So angle preserving maps, angle preserving diffeomorphisms, they are called conformal maps. So now what happens is we will look at all conformal maps and we will show that they are Mobius transforms. So first we proved that isometries are, or we have conformal, we have this. We will prove that this, we will prove this is, so we will prove that the conformal maps are also are just Mobius actually. I will actually not prove this. I will just say this because this is a difficult theorem to prove. So okay, so it will be enough for us if we prove that all conformal automorphisms of the disk are Mobius maps. One other fact you should know is so this is one fact which I will just use without proving. The conformal maps will be biholomorphic. So once you have this, you will just get, we know that all biholomorphisms of the disk are the Mobius transforms. Okay, this is okay. Yeah. So this will be using Schwartz lemma. So this proof is slightly has a lot of holes, but one thing you should know is all orientation preserving isometries are just this. This is the most important part you should know. Proof can be found. There are elementary ways to prove this also, but slightly longer. Anyway, another theorem I will state is so this hyperbolic metric which we defined, we know that that is invariant under our Mobius transforms. but this is also the only metric which is invariant under the Mobius transforms, unique up to some scaling factor. Okay. Again, this is not really important. I just wanted to state this. Yeah. Okay. After now we move on to area. So up to now we have just been discussing about we had a Riemannian metric which gave us a way to measure lengths of curves. Using the length of curves, we were able to define distance. Now using the same Riemannian metric, we can also define a area form so that we can talk about area and volume. So so the area form for our upper half space will be dx dy by y square. Um, so on the disk, it will be 4. So in general, so if you have a general Riemannian metric like this, the area form okay, given a general Riemannian metric, the area form will be defined to be this. There is a reason why we take this extra square root of Eg minus f square instead of just taking dx dy, but that is for like manifolds in general. This so just remember this is a natural kind of thing defined by the metric. So now we have a form which we can integrate over like disks or any other subsurface of the hyperbolic space. So in particular, geometry is interested in triangles. So if we look at the hyperbolic disk, triangles could be anything, right? Anything with 3 sides. But normally, when we do Euclidean geometry, we want triangles which have sides as straight lines, not any random squeezy lines like this, right? So what are straight lines in our setting? So straight lines are geodesics. So I will call the special triangles here as geodesic triangles. So in the disk, the triangle will look like parts of a circle. In the upper half space, the triangles will look like things like this, parts of circles. Okay. So there is a special triangle in the upper half space, in the hyperbolic space called ideal triangle. Okay, so ideal triangles will be triangles which seem to have vertices on the boundary. So those will be something like this. Okay, this is in the disk. In the upper half space, you'll have things like this. So these two go up and meet at infinity. So this is still a triangle. Okay. Of course, there are there are other types of triangles also. So you can have two vertices at infinity and one inside, or you can have one vertex at infinity and two inside. Okay, these will all be triangles for us. So now I claim that these ideal triangles which I defined, they are unique up to isometry. That is, if you give any two ideal triangles, I can find an isometry taking one to the other. Okay, so okay, so the proof goes like this. So first note that if you have any 2 points on the boundary, if you have any 2 points, there will be a unique geodesic kind of connecting these 2 points. Okay, so the geodesic doesn't actually go through these 2 points. It's just those are points at infinity you can think of. Okay. So now, so so if you give any 3 points, 3 distinct points on the boundary disk, boundary circle, so I will have a unique ideal triangle determined. So you take 2 points and draw geodesics between them, then you get a unique ideal triangle. Similarly, so any triangle, any ideal triangle, uh, So if you have any ideal triangle, you will of course get a unique triple of points on the disk. So there is like a one-to-one correspondence. So you take distinct triples from the boundary. Each of them gives you ideal triangle. Each ideal triangle gives you a triple. Okay, so I will just move between each other now. So now what happens? We are given two ideal triangles. We want to take one to the other. So right. So T1 gives so T1 gives 3 points belonging to delta D. Right. So just know that delta D is also delta H. Okay. As in the boundary circle from the disk you get is the same as R union infinity. Okay. Just keep that in mind. So now we had proved that initially that given any 3 points on your boundary, our PSL2R acts transitively between them. So by So we now have a PSL2R matrix, a Mobius transform taking A1, B1, C1 to A2, B2, C2. So you can verify that this isometry, this this Mobius map, which is also an isometry, okay, it will take for the first triangle to the second triangle. Okay. So since our area form was defined using the Riemannian metric, and Riemannian metric is preserved by the isometry, area will also be preserved by isometry. So a corollary we have is since we proved all ideal triangles are isometric, we have also proved that the area of all those triangles is the same. So what is that area? I claim the area of ideal triangles is pi. How do you prove that? You take any ideal triangle. So I will do it in the upper half space. This is our ideal triangle. So if you do this integration, you will get the value to be pi. Okay, so we have seen that we have proved now that all ideal triangles have area pi. Now let us calculate area of other triangles, like other triangles whose angles are like alpha 1, alpha 2. Okay, so we will look at a general triangle now. Also note here that if alpha 1 equal to 0, this will be an ideal triangle. So alpha 1 can only be 0 when this point is here. Okay. So in hyperbolic space, we can have triangles which have 0 angles as well. Okay.
So the map you took from the upper half plane to the disk, was it an isometry?
Yeah. So by definition, it happened to actually no. Yeah, it will be an isometry. It is like z minus I by z plus I. It is also a Mobius map. If you like pull it back, if you pull back the metric, you will see it is.
Okay.
You can also think of it as you take the upper half space, then this is a map taking you to the disk, right? So you have a metric on the upper half space, you can just pull it back to the disk. That is how I actually got the metric. That metric didn't just like pop out of nowhere. Okay. So yeah, so in hyperbolic geometry, you can have triangles with 0 angle. Okay. Oh yeah, let me make it clear why this angle is 0. So since geodesics are all circles or parts of circles which make 90-degree with this tangent here. So a geodesic triangle is made of ideal triangle is made of geodesics like this, and this geodesic also makes angle 90 over here. So there is nothing left here anymore. This will be 0. Okay, just note. So so if you have any triangle with angles alpha 1, alpha 2, alpha 3, then your area will be this. Okay, this I will not prove this. This is slightly harder to prove. But one important thing you should notice, I am not talking about the length of the sides anywhere. We are just looking at the angles and we are able to calculate the area. Okay, that is a key factor you should notice. So So we don't need length of the sides to calculate area, just the angles are enough. This also means that given any two triangles which have same angles or which are similar, then their area must be equal. It can also be proved that they will be congruent. Basically, like you give any triangle with alpha 1, alpha 2, alpha 3 um, as their angles, you can find an isometry taking one to the other. So basically what I'm saying now is the length of your sides are also fixed here. Once you fix the angles, the length of the sides are also fixed. So in hyperbolic geometry, there is a sort of rigidity given by angle. Now it is not as flexible as Euclidean space. Okay. Also, uh, we should also know that alpha 1 plus alpha 2. So this sum is always less than pi, so that, I mean, this is an independent consequence. This so this comes from the fact that there are infinitely many parallel lines. Okay, so this is an independent fact, and because of this formula here also makes sense, so that area is not negative at any point. Okay. So now curvature. So curvature has as defined in normal textbooks in differential geometry. The Gaussian curvature has some very weird formula involving the first fundamental form. But there is also a nicer form when our metric is like this. Or so for any conformal metric, that is metrics of this form on R2 or whatever subset of R2, the Gaussian curvature so the Gaussian curvature is given by k at any point z will be negative. This is the Laplacian. Okay, so if you have, if this is your metric, you take that row and do take this partial differentiation, then whatever you get will be the curvature at the point z. So Um, So if you just do this calculation, you will see that the hyperbolic metric, it has -1 curvature at every point. Okay. So right now it seems like this is just a consequence, but this is one of the most important properties of hyperbolic space. This is also like the defining property of hyperbolic space. What do I mean by defining property? So this is also theorem I will not prove, but very important. So basically, if you have any Riemann, any two manifold with a Riemannian metric, so that Riemannian metric will have curvature at every point, and I will say let the curvature be -1, and I will also ask that the manifold be simply connected and the metric be complete. If you have all these properties, then your space will be isometric to the upper half space. So basically, like this -1 curvature is a defining property here. If I put, instead of -1, if I put 0 curvature, then we will get the Euclidean space R2 with the like standard metric. Then if I if I put +1 here, let me just write it. So if I have +1 and everything else same, then I will get the sphere. Okay, sphere with the usual metric. Okay. So this is, these other spaces also have names. So this upper half space is hyperbolic. This is flat. Okay. These are three important geometries in 2 dimensions, or these are the only 3 geometry. Okay, like whatever we are doing right now, like talking about triangles, we will also be doing trigonometry. We can obviously do that in R2. We can also do that in the sphere also, and the formulas actually look same. Okay, so are there any questions?